So today's topic is machine learning for fraud detection and anti-money laundering, or in more technical terms, how to catch bad guys with AI. I was already introduced. My name is Solomiya. I catch bad guys with AI at Moniz for almost 2 years now. For those who didn't know, Moniz is a mobile bank. Or digital bank, how they call it, or how we like calling ourselves, challenger bank, because we challenge big traditional banks. If you've never heard of Moniz, you might have heard of N26 or Revolut or Monzo, etc. It's a very recent thing. And the point about those mobile banks is that it's only a mobile app. We don't have physical branches, and we make life much easier for people who have troubles opening their bank account in traditional normal banks. Because for us to open a bank account, you just basically need to install the app, to fill a small form, some small application, to take a picture of your ID. And this is it basically. And you have your fully working bank account. You can have the one, like the different digital banks do different things, but mostly you can open the UK account, a European account, with some cases, like with us, you can also have, for example, a Romanian account. Okay, so yep, this is what we're gonna talk today about. I will explain a little bit of theory, what are the types of fraud the digital banks are concerned about. Okay, maybe before that, to understand actually who is here, who is listening to me, can you please, either you can use chat and write what do you do for your, like what your interests are, or what do you do at work, what would be, and maybe like what your expectations could be from this workshop. Or for those who are, let's say, data scientists, can you please do yes or thumbs up, something positive in the chat or in the participants? Yeah, I will take 10 seconds lag to calculate. Okay, nice. There are a couple of people. And then who of you works in fintech? But doesn't deal with AML, doesn't deal with anti-money laundering? Nice, also several. And then please also let me know if you deal with anti-money laundering, fraud detection, risk, maybe some risk predictions, maybe some sanctions tests, sanctions and so on. We have like a different small groups of people, I see. So I really will try to make it easy to understand for everyone, and so data scientists have something useful to bring from today, and then for other people too. So my goal is to basically, if you have to build a machine learning model for anti-money laundering yourself, you can basically kind of follow this guide on a general level, or if you will have a data scientist or someone building it for you, then you will have some hints what to talk about them, how to understand them, what kind of language they speak, and so on. So is everything fine? Can we start? Let me see the chat. Okay, chat is thanks. Chat is empty now. You can just write what you want, what's on your mind in the chat. You can also ask your questions in the chat, or we'll do Q&A later. Just talking to each other. If there is something really unclear, there's not many of us, so we can have more or less individual approach. If it's something really unclear, feel free to break me and say, go back to the last slide, or I don't really understand, can you explain it again? Because I really want for everyone to be it very useful. So I will start with theory. I will explain what kind of fraud challenger banks care about, what is money laundering, how fraud and money laundering looks like, And then I will explain a little bit what is the process of data science, how the model building looks like, what other steps, and then I will go through each of the steps, explaining a little bit more why it's different for AML, for example. What's actually important, and then I will just emphasize some other important things that don't really fit into any of the previous points, but I still find them very useful. And then we will do Q&A session. So again, if you in order to not forget your question, you can write it in the chat. I will go through the chat later, or in the end you can just raise your hand and Heike will let you in and we can have a chat between us. Okay, sounds good. Let's start. I might in the middle. I might also be asking you to engage with me, to interact a little bit. So if you lose me, then you might be lost for more time. Please do thumbs up if it looks okay and if you can start. Well, I see some other people are joining. So let's start with the theory. There are two biggest types of fraud that the banks are very concerned about. The first one is the credit card fraud. It's when someone uses victim credit or debit card or credit account to make a purchase they didn't authorize. Basically, someone steals your credit card or steals your credit card credentials and buys some goods that you didn't authorize. The another one, APP fraud, authorized push payment fraud, as clear from the name. It's the opposite. It's when the victim is manipulated into making payments, so it is authorized. You, as a victim, are manipulated into making payments to fraudsters. Often, it is done by social engineering attacks and involves impersonalization. From the point of view of big banks, they are looking from the victim's point of view, because so what they are trying to do, mostly they are trying to understand which transaction is not authorized by the victim or looks like it shouldn't be done by the victim. So they try to catch those. It is not such a big problem for challenger banks, because our customers who are able to download an app, to do everything online, they are probably tend to be more digitally, technologically educated. So they know a little bit more about internet security, about data, the security of their data. So they tend to be harder to fool or to scam, basically. But as I told already, digital banks are making life easier, life easier for everyone, including fraudsters. So what do we care about a lot is how to not become a hub for fraudsters or for money launderers, because it is very easy to open an account, which means it is very easy to use it for bad things as well as good things. So if you do a credit card fraud, it is hardly trackable, because you as a person, you just use other people's credit card. But if you do APP fraud, authorized push payment fraud, you need to have an account which your victims are going to be sending money to, right? So this is what we are looking a lot, we are trying to catch a lot and as fast as possible in the challenger banks. Let's talk a little bit in details about APP fraud, why it's such a problem. It is a real problem. I'll give here the UK data, because UK is one of the countries, that they have a very good data on it. They gather a lot of data on APP fraud, so they have detailed statistics. It's nice to see the scope. So yeah, in 2018, more than £300 million was lost through APP frauds. In cases, total number of cases comparing to the year before, it's doubled. In money, it was 50% growth. The APP fraud is 30% of total fraud in the UK. The 90% of the APP fraud is committed on digital channels. And yeah, and there are different types of it. There are different ways. the fraudsters can do it. For example, the CEO fraud. When your so-called fake CEO calls you or sends you an email saying like, hey, I need a favor, I need this I need right now money as soon as possible to be transferred to my account. And then you've been like, whoa, the whole CEO calling to me. So often you cannot recognize that the email looks kind of fake, or the phone number is wrong, or so on. So to be aware of that. There are also goods that are not received. So many fake tickets, fake iPhones are sold on the internet when the victim basically just sends the money and then never gets the goods. There is also fake invoices when it happens a lot to accountants, when the fraud team that looks like one of your business partners, they just send you an invoices. And if you're a big company and if you have thousands of invoices per month, and you can easily let that slide. There is investment scams when some Nigerian fraudsters often say that they are royal. They say that they want to transfer the money from Nigeria to, let's say, Europe, and they need you for that because you have a European account, and they offer you a good money for that. But when you transfer them the deposit, some money to cover the transfer, then obviously they just disappear, and you never see your money again. As well, there are rental scams when you send a deposit, but there is no rent at all, there is no existing flat. There are beneficiary account change when it looks like your partner in business sends you an email saying we are changing all the accounts, please all the following payments due to those accounts, which is, it might not be true. So it's important to be aware of that. So now you know how it works. If you look at the fraudulent account, if you have a fraudster in your bank and you look at their account, then you see many incoming payments from third parties. Often in the reference there is invoice number, so people think that those are real invoices, and they are very quickly followed by outgoing transfers and or cash withdrawals. How do we call it? We call it in the AML team, we call it cash in, cash out. Okay, enough about fraud, and now a little bit about money laundering. Let's imagine you sell some drugs, or you got a bribe, or you sell weapons, or you do some terrorist activity. Anyway, you have some illegal money. If you want to buy a house with those money, you cannot just put all those cash in the suitcase and come with the suitcase to the seller, right? They're going to have a lot of questions. So what you want to do is you want to make it look like this money is legal. So this is what money laundering is. It's an act of concealing the identity of source of money obtained in an illegal way in order to make them look like they're legally obtained, so it can be used without suspicion. Yes, how does it look like? After you got your money, you sold your drugs, you do placement. You want this dirty money integrate into financial system. So you break your whole amount into small amounts, and you can ask your friends, you can pay some poor students, you can do many other things for those small amounts to enter the banking system. If it's a small deposit, 500 euros, no one cares about that, right? Then you start moving this money around from bank to bank, from country to country, between different banks, different countries, different continents. You're trying to make it very difficult to trace this money, how it is, what was it moving. And then finally, when, let's say, the money is untraceable, you can get them back. You can, for example, go to the casino, the fake casino, and ask a fake casino to send you the money to your account, which is going to look like it's luck. You got it legally, just luck. So then you can easily go and buy your house that you wanted to buy, or anything else, any luxury assets or in dust or anything you want. So if you have a money launderer in your bank, how does it look like? First of all, there is going to be several things that are typical for money laundering accounts. It doesn't mean that they all are in place. There might be one of them or two of them. So there is a lot of work to catch them. First of all, there are regular ATM withdrawals. There are bursts of activities in a short period of time. Usually a bunch of money have to be laundered quickly. It's laundered, it's done. Many cash deposits are broken down to sums below the reporting threshold and then deposited in multiple banks under different names. This is what I was just explaining about one of the ways. There can be cash withdrawals from one bank in one place, redepositing the same cash in the bank in another place, and then transferring it to the third location, who will do the same. There might be various direct bank transfers from country to country, especially between to the banks where the to those countries that are protected by secrecy law. Also, casino is a very risky place, and as the banks try to look at all the casino transfers to understand if the money is actually won by the customer or it's money laundering. All right, so now knowing all this information, we have to build our model. In order, there are several steps that it takes. First one, I'm going to explain shortly each of them. What does it mean? We're going to talk about some terminology so we are on the same page and we know what everything means. And then I will go through it one by one, emphasizing what's important for AML. So let's start with feature engineering. For the first step, when you build a model, you basically want to build your data set. And in this data set, you will have variables for each client, for example, such as age, address, email, transaction data, and so on. And those variables or columns or predictors, we call them in data science, we mostly call them features. It's like this part might be very easy for data scientists. So yeah, I apologize if it's too obvious. I hope you will get, for yourself, you will get to know something more interesting during maybe feature engineering, for example, like those information. But yeah, to try to keep everyone engaged and trying to make everyone understand, I'll go through some very simple details for data scientists or some cool things to know for not data scientists. So yeah. We call them features. Age is a feature, address can be feature, but feature should be engineered. You cannot just take the whole address and what everyone's supposed to do with the whole address. You can make it so that it's going to be easy to make some rules based on it, to predict based on it. Then, so yes, columns, they are variables, or how we call them, features. Then the last column, mostly, these are labels. Labels is what is, like, usually they are zeros or one. If it's a classification task, there might be more class, might be more groups, but in AML it's mostly zeros E1, zero fraud, zero not fraud, sorry, zero good customer, genuine customer, one fraud, or zero good customer, one money laundering. So this column that says what do we want to predict, we call them labels. Now in AML there are a lot of static rules. Before machine learning was introduced, became popular, what banks were doing, they were just doing simple static rules. For example, if the customer made a transaction that is more than 10,000 euros, flag an alert. That's an alert, let's check this customer. Obviously, when you have thousands, hundreds of thousands, millions of customers, those approaches are extremely ineffective. They give out of those couple of very small amount of fraudsters that they catch, they have a lot of very, very many good customers, because obviously a lot of people do transactions, might need to do a transaction that is more than 10K. So now when we have a lot of computational power and algorithm to use with it, we can do more complicated things with AML and build machine learning models. So when we have our database with our features and our labels, we divide it to train test and test set, train set and test set, sorry. Usually, we will, for training the model, we will leave approximately 70–80% of the data, and for testing the model, we will leave another 20 or 30% to actually take a look. So with testing it, we will be able to see how the model performs in close to real life circumstances, and we can. This way, we can also compare different models, testing them on the same test set. So train set and test set. Now, the next step, we do the training of the model. We take the train set, those 80% of the data, we feed it to some model, to some algorithm that is gonna do learning for us. It's gonna learn what kind of linear or non-linear relationships are between those features so they can predict the labels. And after that, after the learning is done, we get our final model. Like one model that says, that can be like just a long set of rules or decision trees or something else. That's one model that tells you that's one basically, that did the best during the training process. And it looks like, so we want to test it. We want to test how it works. Then we take the test data and feed it to this model. What do we get? For each customers that we, for example, in our previous case, we had customer number 1 and number 2 in the training set and customer number 3 in the test set. So in the end, after we feed the test data to the model, we receive for each customer from the test data, we receive a score. Often it is from 0 to 1, and it's something similar to the probabilities. I see the chat message. Are your labels noisy or you assume they're not? Thank you. I'll do later through the chat. So yeah, we have labels. Yeah, okay, no, we have scores. So score is kind of similar to the probability. You can, it's not quite, but you can think about it. The higher is the score, the bigger is the chance that this person is doing fraud or doing money laundering. What do we do next? We take some, we decide to test some threshold. Let's say, we say that, but for those customers, right, that on our test set, we have the score, so how the model thinks, what the model thinks, and we have the real data. We actually know who they are they fraudsters or not? So we take some threshold, let's say 0.9 or 0.8, and we say that everyone who exceeds the threshold is going to be classified, according to our model, as fraudsters. Everyone who is below the threshold is going to be classified as a good customer. So we can actually, we can take all those that model classified as fraudsters and see how many of them are the real fraudsters, for example, and how many are good customers and so on. But I will talk a little bit also in details later. So as a result of each model gives us a score. And in the end, if we evaluated it and we are happy with our model, we want to deploy it. To deploy it basically means to make it run automatically. So let's talk about all those steps a little bit more in details. About features. Today I will describe 3 main groups of features, which I call them profile features, transaction features, and benefits features. Profile features and transactions features are those that are highly used in this field by data scientists who do AML. Benefits features, it's kind of the area of my research. I was writing my master's about it. They are a little bit different. They are not that used yet, but I think they have a potential. So I'm going to explain them. I proved that they have a potential. So I'll explain a little bit about them as well. yeah, some kind of a bonus features, a cool stuff. Okay, let's start with profile features. Such features as address, for example. We all know that somewhere in Bronx, there are more criminal areas than on Manhattan, right? So we can simply use this the same with London. East London is more associated with crime and fraud. So we can simply use address, the area or the street, for example, the city and the street. We can use also age. If it's a challenger bank, then yeah, younger people tend usually to be more associated with fraud. Gender, we can allow to use it, but from my experience, gender doesn't really matter. It's just not a significant feature. Then there is document issuing country. For challenger banks, it is hard to have a citizenship. So what we can use is a document issuing country. It's not the same as citizenship, but at least it can give us some more information. And document type was the type of ID that customer used while onboarding. Why it has predictive power, because, for example, if you're a fraudster, you obviously don't want to take a picture of your real passport, and to onboard with the bank if you're planning to do fraud or money laundering. So you will use, for example, a provisional driving license, just driving license. So the document type also matters. Device models matter, so I cannot explain that, but there are some more popular device models. It also works in the nonlinear relationship. Geolocation also matters. Changes in geolocation. If the customer withdrew money from Europe, and in 5 minutes they withdraw money from some other country, that's, unless customer knows how to teleport, that's obviously not possible. These were more obvious ones. These are a little bit less obvious, but it also might work. For example, account creation relative hour, like when the account was created, might be in the night, I don't know why, or might be in the morning for fraud. For usual people, if they are working, they're probably doing it in the evening, right? But fraudsters, they have a full day, for example, as well as relative day of the month when the account was creation. Some fraud is actually kind of seasonal. So some weeks of the month are more active as fraudsters. For example, the salary receiving day, right? When people have money to spend and to buy not a fake iPhone, but to buy an iPhone and to not get it. Then there is email. You can use domain if it's like a genuine domain or not. And the first part of the email, such as, for example, fraction of numbers, fraction of vowels, entropy of email, how bizarre is it? Yes, how normal it looks like. Then there are the number of devices used while onboarding, for example. If people switch devices drastically several times, it means that something weird might be going on. Or also if the address that they add is unique. Sometimes if you are a criminal, if you want to withdraw cash, you need a card. To get a card, you have to have an address. So many gangs, bands, criminal gangs using this same flat, basically same address to receive all their cards. Now there are also transaction features. First of all, we can use some information from the single transaction, which is like transaction amount, transaction location, time difference to previous transaction, how many zero count, how many zeros are in the transaction, transaction type, for example, as well. As like now we know that, for example, such transaction types as cash withdrawal or direct transfer are more associated with fraud. Then you can calculate some statistics for customers since the very beginning of their customer journey, or for the last year, last month, last 2 weeks, last week. You can have a rolling window calculating, for example, what is the sum of the amounts of the transaction that come in and out. How many of the transactions come in and out? What is the average number? What is the mean or the standard deviation of the transaction amount? What is the a standard deviation of number of zeros. If it's like all the transactions are, I know, plus 1,000, minus 1,000, plus 1,000, 1,000, minus 1,000, then people don't usually behave like that. You can also do the same for specific transaction types, like what is the count of ATM withdrawals, what is the sum of ATM withdrawals, mean, standard deviation, the same with direct transfers. What is the proportion of different transaction type? For example, what is the percentage of, what is the fraction of transactions that are incoming transaction, and what's the part of fraction of outgoing transactions? Why it makes sense? Because, for example, if I receive a salary, then I will have, and like I'm a good customer, I'm just using my bank in a normal way, I will receive a salary. It's going to be one incoming payment, maybe like some friends owe me money, I don't know, 2 or 3 incoming payments. And then all my payments are going to be outgoing because I spend my salary, I buy stuff, and I pay for utilities. So yeah, if it's, but in fraudulent cases, money laundering cases, it's more to 50-50. And there are some other features like account age, account balance, profile changes, and so on. The third type of features, they're actually very easy to calculate. I will first explain how to calculate them, and then I will explain why would we do it at all. So we want to see what fraction, how many transactions for each customer, how many transactions start with 1, for example, 1 euro, 10 euros, 20, not 20, 10, 15, 100, 150, and so on. How many, what percentage of transactions start with 1? What percentage of transactions start with 2, being like 20, 25, 200, 2000, something, and so on. With 3, with 4, with 5, up to 9. And we want to have the same, and also 0, and we want to have the same for the second digit. Like, yeah, for example, if the second digit is 0, it means that it's a round number, right? For example, 20 or 200, it's going to have the second digit 0. So what percentage of fraction have the second digit? 0, 1, 2, 3, up to 9. Yes, for example, we have a customer that made three transactions. Customer ID number 1, 3 transactions. Transaction amounts doesn't matter if they are incoming or outgoing, doesn't matter the currency, doesn't matter as well. Let's say we have 7.4, 50, and 45. So we can just have, we can see that the 1/3 of customers, one transaction starts with 1, it's going to be 0.33, and then 1/3 start with 4, 1/3 start with 7, 2/3 have the second digit 5, and so on. So this is how we can basically build our features. Now I have the question to the audience. What do you think is going to be, like, for an average customer who has many transactions, what do you think will be the distributions? How do you think those digits are going to be distributed? Yeah, let's, I'll give you half a minute or something to write your ideas in the chat if you want to, if you know the answer. If you know the answer, then don't tell it. How do you think? So again, if we calculate what percentage for the customer starts with 1, with 2, with 3, with 4, and so on, what would be the final distribution? Anyone? Okay, who thinks that the final distribution is going to be even? Like, it's going to be equal amount of different transactions that start with different numbers. I do. If you asked me about that, I would definitely think, okay, but they're going to be like 10% of each of them. What's the point of doing this? Some people say that might be normally distributed. around 5 or something. Half normal maybe, yeah, skewed. Yeah, so they are actually going to be so-called Banford distributed. There is this really cool law called Banford's law that says that in naturally occurring numbers, the first figure is oftener 1 than any other digits, and the frequency diminishes up to 9. So in 30%, that's the theory, might be, according to the law, and the law works for many, many cases, for example, the population of cities and countries. Around 30% of all countries, as we can see the first bar, 30%, is going to have the population that starts with 1, like 1 million, 11 million, I don't know, 15 million, 100 million. And then around 17 is going to start with 2, and then it diminishes up to 9. It works for many different data sets. The Banford itself, who was checking this law, he checked I think lengths or areas of the rivers. He checked the streets numbers, numbers of the houses of the streets length, and so on. And then there were a lot of other people who checked that as well. For example, on daily stocks, file sizes on your laptop is most probably also this kind of distributed. US crime statistics, financial data for different industries, financial single reports, population of towns, towns and cities, I have it twice, tax income data, citations received by papers, electoral data on votes, survey data, deficit data. Sometimes it doesn't work, but often it does work. So when I was working on this topic, I wanted to see, does it really work for transaction data? Can we make an assumption that the average client is gonna, his or her transactions are gonna be Banford's distributed? When I think about my own transactions, I'm not sure, maybe. I have no idea how my transactions are distributed and what do they start with. So yes, I decided to check that. So I took all the transactions, from all the people for our bank, from Moniz, for a year or maybe 1.5 years, for some period of time. I took the first digit for each of them, and then I plotted them. And this is how it looks like. The blue, so on the x-axis, there is digit 1, 2, 3, 4, 5. And then on the y-axis, these are frequencies. The blue bar is the one that I've actually seen in my bank, have the real data, and then red bar is the one that we would expect according to the Banford distribution. And I was really, really surprised that that follows the distribution very, very well. It cannot follow it, the point is not to follow it 100% well, because the point is a monotonic decline. And of course it cannot be very strict, because in the bank we have zeros. We have transactions that are less than 1, that start with 0. So it cannot be exactly, but even this, I was really surprised that worked. I didn't believe in that. So yeah, now we know all of that. I hope it makes sense to calculate how many transactions, so what the percentage of transactions start with 1, 2, and 3. But if we, I have another slide why it works. I'm not sure. It took some time already. So we will, if you have time in the end, we can go to it. And there are several hypotheses why it works. But let's move back to features. So in order to calculate some additional features, to add some more additional power, predictional power, we can calculate the different types of distances between our observed distribution that we see for each specific customer and the expected distribution that we would expect according to Banford, like Euclidean distance, chi-square distance, Chebyshev distance. There is a whole bunch of different distances in the literature, so we can also use them. Okay, now when we have our data set, we have our bunch of features, probably more than 100, maybe a couple of hundreds. We have to build a model, basically. I will not be going in deep here because there is an enormous amount of different algorithms that you can use in data science. I can just tell from my experience that those algorithms that work based on the decision trees, they work the well. XGBoost rules. XGBoost is always the best so far, and I think it's going to be for a while now. This is if you have actually labels. In case of victims, we do have labels of APP fraud. The labels are good. There was a question. The labels are good because there is a victim. The victim, which is scammed, just comes to the bank and says, hello, I didn't receive my goods, I'm scammed. So the bank does really, with the high probability, they know that this is the fraud, this is APP fraud. In case of money laundering, it's not that easy, and the data and the labels are more noisy, yes, because we don't really know if it's money laundering or not. Banks are obliged to report suspicious activity to the national crime agencies. So the only information they get to have their labels, they can have maybe some emails from another banks that say, listen, there is something weird going on with this account. Can you please check? Can you investigative check? There are also static rules, as I told you before. The easy rules, from them we've got some information about money laundering. But yeah, the national crime agencies never give a feedback. They don't say, okay, that turned out to be money laundering and that not. You just have to report all suspicious activity. But still, these are kind of labels. And then, so if the XGBoost or the other tree-based algorithm work if there are labels, it's a classification task. If you don't have any labels at all, you can try doing some anomaly detection with there is isolation forest, for example, that might work, or there is you can do some clustering and try to identify small fraudulent or money laundering clusters. Yeah, so we try different algorithms. And then we want to assess them. We want to evaluate how well it works. For that, it's all obvious for data scientists. But if you're not a data scientist, or if you want to do it yourself, it might be useful for you. Or if you will have a data scientist doing it for you, it is also very nice to know, because we data scientists, we know how to make bad stuff look good. So in order not to fool not to let anyone fool you, it's nice to know about the evaluation of the models. Let's say this is our data set, our test data set. And those ones on the left, these are our fraudsters, relevant elements, our fraudsters. On the right, we see good customers. Of course, the balance in different is in real life data, but just an example. So fraudsters on the left, I'm trying to not confuse anything. Real customers, good customers on the right, and then in the circle we see all the customers that model picked up as fraudsters. That model think that they are fraudsters. So some of them are actually fraudsters; they are true positives. Some of them are not fraudsters; they are good customers. So they are false positives. By knowing this, we can calculate several coefficients, which will tell something to us. First of all, the most famous one is accuracy. It's when you take out of all the customers, we calculate how many of them we correctly predicted. Yes. For example, in this case, we would have to divide for all of them and take those true positives ones and true negatives. We would do true negatives, the gray area, plus the bright green area, divided by all of them. Then there is precision, which tells us out of all the customers that model thinks they are fraudsters, how many of them are actually fraudsters. So these are this green area divided by the whole circle. Then there is sensitivity or recall, which says out of all fraudsters, how many of them the model was able to pick up. So the true positives divided by all of the all of the fraudsters or positive elements. And there is specificity, which says that out of all good customers, how many of them were correctly classified as good customers. So out of all good customers, how many of them model classified as good customers. Now, just a simple example. Let's calculate it to have some rest. Let's say our test set is 1,000 customers. We know that the 10% of them are 10 of them are fraudsters, so 1% of them, 10 are fraudsters, and the rest 990 are good customers. We take our model, we pick the threshold. Let's say we say that everyone who is above 0.95, we classify them as fraudsters, and everyone below 0.95, we classify them as good customer. And then we see, we take all those people who are more than 0.95, and let's say we have 20 of them. We investigate them, we check them, we see, and out of those 20, 5 of them are fraudsters and 15 of them are good customers. So basically we were able to find out the half, to pick up the half of the fraudsters, and then we have some false positives, good customers that were picked up by the model. Let's now calculate those coefficients that I was talking about. For example, accuracy, how many we were able to accurately predict. We did the good job with 5 fraudsters and 975 good customers. 990 minus 15 is going to be 975 plus 5 divided by 1,000, accuracy 98%. Yay, looks cool, sounds promising. Let's calculate the precision. Again, out of all the alerts, out of all the customers that model thinks they are fraudsters, how many of them are actually fraudsters? In our case, it is 5 fraudsters out of 20 that were out of all that were picked up by the model. So it's 25% precision. Now let's do sensitivity or recall. So out of all fraudsters, how many the model was able to identify, to pick up. We had 10 fraudsters, the model picked up 5 fraudsters, so 5 out of 10 is 50%. And let's do specificity. So out of all the good customers, how many the model was able to identify correctly. So we had 975 good customers not picked up by the model as good. Divided by all the customers, it's 98% specificity. Right now, we did it for the 0.95 threshold, right? If we do the same, for example, for 0.9, we're going to have a little bit different results. We're going to have more model picked up overall, more alerts. Probably we're going to have more fraudsters, or I don't know. We have basically all those coefficients we can calculate for each of the threshold. We can start with 0.01 and classify everyone above 0.01 as fraud, below as good customers, and then we will obviously catch all the fraudsters, but we will have so many good customers there. And then so we can calculate those coefficients for each one of them from 0 to 100 in order to and it's a lot of work. You cannot just have 1,000 coefficients or something. So to do that, we can actually plot it. Each coefficient is 1 dot. For example, let's take precision and recall. We had our precision 25% for this threshold. 25%. We had our recall 50%. Let's say if we plot it, it's going to be just 1 dot, 25 precision somewhere here and 50% recall somewhere here. Our dot would be somewhere here. So one threshold is 1 dot, and for each of the thresholds we can calculate the precision and recall. And if we do that, it's going to be, we call it precision recall curve. What we want to do after that was that we want to measure the area under the curve, and the bigger is the area, the better is the classifier, of course, because we want precision to be the best and recall to be the best at the same time. So the bigger they both are, the better it is for us. Why I'm saying this? Because in data science, the most popular way to measure to measure the performance of the model is not precision recall curve, but it's ROC curve. It's similar. You call recall or sensitivity as we're talking on the y-axis, and then we talk y minus specificity on the x-axis. Y minus specificity is basically what? It's basically how many out of all good customers, how many were actually picked up as fraudsters. Yes. So it's an opposite to specificity. So if we identify 98 of good customers correct, then we identified approximately 2% of good customers incorrect. So if we plot that, we're going to have our ROC curve. And it's a very, very, very popular way. It's like the most popular way among data scientists to measure it this way. But I wanted to show that in AML, it is much better to use the precision recall curve because the data is so imbalanced. The data is imbalanced means that there is very small amount of fraudsters and a lot of good customers. So this is the real life example. For example, when this area under the ROC curve in both cases is high, in this case 0.89, cool. In this case, these are two different models that were doing different tasks, both highly imbalanced. So the second one is 0.93. Looks very cool. Both of them work very well, good. Data scientists would be happy, but if you look at the precision and recall curve, they are drastically different. One of them is 0.13 and another one is 0.55. This is because of imbalance, and because in AML we care about positive, we care about like one group of customers which are fraudsters and which are minority. I also wanted to say about the accuracy. You remember in our case we had 98% accuracy. This accuracy cannot really be used in AML because it is, let's say that we decide, in our case, we decide that our classifier, our model, says that everyone is a good customer. Just our model is the way it is. It says everyone is a good customer. In this case, in our case, what we would have, we say everyone is a good customer, so we classify 990 people. So 990 out of 1,000 people we would classify correctly who are actually good customers. So our accuracy would be 99%. Sounds cool, 99%. It doesn't detect any fraud. It doesn't do anything. It just classifies everyone as a good customer. So that's why this is the danger, and not to forget about it. If you read some articles and they don't report in their article, AML article, and they don't report the accuracy, they report only accuracy, and they don't say how many of what is the balance, how many of the customers are fraudsters, how are not, what percentage of them, then it doesn't really say anything. Yeah, so that was about the evaluation. I personally like the most the precision and recall curve. It tells me the most, and you can also see you can see that with one threshold you can have, let's say, 0.6 recall and 40% precision, and then in another case you can have, let's say, 20% recall, so you'll catch only 20% of the fraudsters with the very high precision, like 85%, for example. For AML, it's very good. And then so we have our model. Let's say we go to the business, we talk to them, we explain them that, and they are saying, all right, the 80% precision and 25% recall is going to be good for us. Let's do it. Let's make it work. So let's talk about the deployment. It's just only one slide. If your model is transaction-based data and you need to have a predictions real time in milliseconds, then you just go to an engineer. So I know ML engineer or backend engineer or some other engineer. It highly varies from what kind of stack of technologies you use, and so on. But if you need batch predictions, for example, like in money laundering case, you don't really have to spot it right away this second. You can do it during the night for the same day that it was before. You can use it's a popular thing to use is Airflow. It's software that lets you schedule your model. So let's say every night at 2 a.m. you say, please get the data from the database, calculate the features, run it through the model, get the predictions. For this threshold, classify them as zeros or ones, below the threshold, above the threshold, and feed it back to the database, for example. So the next morning, then investigators can go and check those people that were picked up by the model. Yes, Airflow. And finally, some other things that don't really suit into the another categories. First of all, when you do data science for AML, it's also very important how many alerts are generated. In AML, the precision is usually very, very low. If you have a static rule and you check every transaction that is more than 10K, for example, then like maybe 5% of them, 3% of them will turn up to be actual money laundering, and all the rest are gonna good people. So for AML, high precision basically almost never happens. It's always very low precision. So let's say if you compare your model to the rule and you say, wow, look at this. I can have the higher precision, like 20% precision, and the rule, let's say, is 10% precision. I can have 20% precision and catch 80% of all the fraudsters. Like, I'm genius, that's awesome. But if you actually do it and you take all the alerts, all the transactions that are going to be above the threshold, it's going to be like, it might be 70% of your transactions, or like even 50% of your transactions. And that's an enormous amount. Your investigators in AML will never be able to identify them, to investigate them. So it is also as additional thing to precision and recall. It is also important to state how many alerts are going to be generated per day, let's say, how many customers we expect to be classified as positives for a day, because otherwise it's simply impossible to check too many transactions or too many customers. Also, when we assess the model, we cannot really see what is the quality of people that are caught by the model. The model two models that you're testing can have slightly different performance. One have some bigger area under the curve, for example. But if you actually go and test and take a look at those people by those two models that were classified positive, you see that one of them is, for example, looking for one types of patterns, and another one is looking for another types of patterns. Like, one of them is looking, for example, catching a lot of international withdrawals and like huge international withdrawals. And another one is just some, I know, minor fraud, some guy sold 2 grams of wheat or something, I don't know, let's say. So yeah, that's important to test, to actually take a look at the people that the model is predicting, because they might just look for different patterns. There's also the common mistake, I guess, which it happened as well in my practice. If your data set is transaction based, so one transaction, one row, and so one customer can have many transactions, right? When you're doing train, test, split, it is crucial to make sure that one customer, all the transactions that belong to one customer, is only in train split or only in test split. Because if the same transactions from this, if the transactions from the same customers end up in two splits, you're gonna have unlikely good results. Once it happened, like a colleague of mine says, look at this, it's the AUC or precision recall core, which is like almost 1. And you're like, no, this is impossible. This just simply cannot be. And yeah, it turned out that some people ended just up in the test split because model the learned on the train, and then it just knew what's going on the test split. So it is important to have a group split if more than one transaction belongs to a customer. Then there is testing. You as a data scientist, I as a data scientist cannot really test myself how well is the model, because I have some domain knowledge and I can have some assumptions, but I have to give them to the AML investigators. And they are subjective. They have different risk appetites, they have different backgrounds, different experience, and so on. And they can come up to the different conclusions. So yeah, it is a good idea to have maybe like at least 3 people testing the same bunch of customers and then averaging the results, unless you have available for you a highly professional AML investigator with many years of experience who doesn't do any mistakes, basically. But yeah, but overall, it is it's a challenge. Another one, data set imbalance. Okay, let's look one more at the kitten, and then I'll remove the picture. As I already told, the amount of fraudsters in the whole data set, out of all customers is very, very small. It's less than 1% often. Often it's less than 0.5%. So the current algorithm that we have in data science, they don't deal very well with this kind of imbalance. And so they tend to be biased towards the major class. Some data scientists use such techniques called undersampling or oversampling, when you, for example, randomly remove some pieces, some customers from the good customers and make them more balanced. Or you kind of come up with the fake bad customers to make it more balanced. But from my experience, that doesn't really work. It speeds up the time of training the model because there's less customers in case of undersampling. But from my experience, it makes the model worse. It makes the final results, the patterns the model catch, significantly worse. So there's no really answer yet to this challenge. Another one is money laundering labels. So as I explained before, with fraud labels, okay, with fraud labels, it's easy because there is a victim reports, we know it's fraud. With money laundering, the labels are actually those customers that our investigators decided to report to the NCA. So in the end, your money laundering model might happen that it is not looking for actual money laundering, but it is looking for the customers that are likely to be reported by the AML team. Also important to keep in mind, maybe no real solution to this problem as well, but just remember, it's important to understand that when you do the model evaluation, your results might not reflect reality that well. They might be biased towards some types of fraud, maybe even biased towards some types of people. If AML agents are discriminating, for example, and so on. And this is it. Thank you for surviving this more than 1 hour and a little bit more. And I can answer the questions now. I think you can just, I promised to go through the chat. Yes, and then you can think about your questions and just, can you unmute yourself? You're probably all on mute, but if you can unmute yourself, then just ask me a question. Are your labels noisy, or you assume they are not? The ADP fraud, as I thought, are not that noisy because you have reports. Some people, of course, might might lie and say, yeah, I was a fraud. I actually received that iPhone, but said that they don't receive, but this is almost never happens. So the fraud labels are noisy. AML labels, fraud labels are not noisy, they're okay. AML labels are more noisy, but it is also possible to maybe to try and minimize the noise in the sense of that very depends on the AML team and how the processes are designed. But in our case, for example, there is the matrix of risk from the lowest to the highest, and they state the number in the matrix in somewhere in the task when they investigate it. So if the risk is so-so, for example, I will not take those labels. If the investigator is not sure, I will not take it as a label, but I'll take those that are actually almost proved to be criminals. How important is email feature in terms of number vowel fraction from your experience? The most important features are transaction features. Then also from what I remember, the important features is type of the document issue and country. Email is somehow important. It's not in the top, but it's not insignificant as well. Okay, if you want to ask the question verbally, but you cannot unmute, please raise your hand and Haik will let you in. Okay, next question. Why are tree-based methods still so popular when deep learning has advanced so much? Because of explainability. Even the tree methods are not that explainable. I can say that it depends on the size of the data set, basically. If it's like, I know, 500,000 customers, then tree method is enough. If it's millions and millions, then it will just take, I know, days or weeks to train the tree-based model. So that's why then you can use deep learning. But from what I've seen from one of the model I built, I also tried deep learning, and there was not much any learning. It was able to learn everything after the first iteration, basically, and then didn't do anything else. So in our case, there is not enough data for deep learning. But you can also perfectly use it because they both catch non-linear relationship. From what extent are you including of your customer details on top of transactional data to find against money laundering? We include basically almost everything that we can get from the know your customer. Know your customers features are basically the profile features, right? That I was talking about. The one that the customer gives us during the onboarding. Yeah, so we use as much as we can. The problem with challenger banks is that there is not too much of the KYC data. We don't know for example, the place where the person works. We don't know their salary. We don't know anything almost about them, because the point is to make life much easier for people. So we don't have that much of KYC data, but we use it as much as we can and trying to get something out of it. If I didn't answer the question, please dial in the end and ask and specify. Do you use graph-based networks looking at transaction between entities? Not yet, but we are working on it. We recently just started working on the graph-based networks, starting with the graph-based database, and then we might. So the first step is to build a database, just to see the network, and then you might be able to maybe train something based on it. But it's a little bit too far ahead in our case. But yeah, it has definitely potential. It even not the network, but the database itself. It has great value for AML investigators. They can just click and see the whole network of this person. It helps even for manual investigation a lot. Have you tried LightGBM, or do you have a comparative assessment of LightGBM versus XGBoost? I would say they are more or less the same. In my case, for some reason, LightGBM simply crashes on my computer. So I wasn't able to use it yet. I know that it should be better. But when I used some of the automatic, automatic data science tools, then they used LightGBM. LightGBM was #1, was the winning algorithm. If I do it automatically with some kind of help of the tool, which has some models pre-written there, they use LightGBM. If I do it myself, I use XGBoost. I'm just used to it. Have you tried AutoML, and if yes, how does it compare to manual developing models? Yes, we did. We tried Data Robot. Data Robot is a great tool, and AutoML is a great tool if you have like a high amount of tasks, and if you want to give access to people that do not have that as deep data science knowledge, then it's great. You don't really have to all know the algorithms or things. You can just test. You can just train the model and test it. From my experience, it was cool because what did I do? I basically decided to check them, how well it works. I took the same data, trained the XGBoost one, for example, on my local machine or on the AWS machine. And use the AutoML platform, and they turned out to be the same. Even though AutoML did it much faster, and they just took they don't really do any parameter search. They just took some basic parameters that they know that work. So yeah, I liked it, even though they are incredibly expensive. So that might be nice for like a big bank, for a startup. They're super expensive, especially now. But if you have extra money, it simplifies life so much easier, and then you can build a model not even writing one single piece of code. I really liked it, honestly. Do you use cloud solutions for deployment, or do it on local service? We don't have local service at all, I think we all do. We do everything on the cloud. We have the whole data security team that works on the kind of all the anonymizing stuff and so on. I cannot tell in details, but I'm not sure if you have. I don't know if you have any local service, but as far as I know, these are all cloud solutions. How do you treat missing values? We don't really have much of the missing values, to be honest. The missing values might be, for example, citizenship, and for some customers we have them, for some don't, but then I simply don't use it. I don't use this feature, I use some other one. So probably, yeah, not even once I did have to do something with missing values. The data quality is okay. Do you also detect group of fraudsters connected to each other using software, or usually AML investigators link them manually? Yes, for now they link them manually, but in future we want to do the network graph database and model. So yeah, we have some plans, but right now they do it manually. Okay, the Zoom questions, chat questions are over. If you also have questions, raise your hand.